All right, periodic motion. First, let's look at circular motion again. So if something's going around in a circle, there's some angle that is increasing with time. And we can say that theta is, as we know, omega t. So omega is the angular velocity of this object that's going around in a circle. Now if you look at just the x component, so that's like right here. So suppose the radius of the circle is a, then the x component is a cosine of omega t. And what's the x component of that object doing? It's just going back and forth in a cosine pattern. So that's a sinusoidal pattern, literally cosinusoidal. So what this represents, actually, you could think of it as there's a light coming up here, and the x component of the object is really just its shadow from the distance from the center. So that's like the x, and the shadow that it makes on the ground. So you're projecting it onto just a one-dimensional line. So this represents simple harmonic motion. That is, if the motion makes a sine wave or cosine wave with respect to time. So simple harmonic motion is related to circular motion because simple harmonic motion is just really the x component of circular motion. So now let's look at what we have for a mass on a spring. For a mass on a spring, okay, there's some equilibrium point. And if you disturb it, like stretch it beyond its equilibrium point, then there's a force. The force of the spring wants to bring it back towards the center. And if you smush it the other way, if you compress it, the force wants it to go the other way. So basically the force is opposite the displacement. And if you remember, the force on the spring is negative kx, where k is the spring constant. So that's Hooke's law. And the question is, what is the motion? So let's find the motion x of t. So how are we going to do that? Well, we could do that by using the fact that F equals ma. So F equals ma. Okay, the force is negative kx. What is a? So recall that a, well, let's start with v. V is position over time. Or we can write it like this, dx dt. And then a is dv dt, which is the second derivative of the position. So we weren't able to do that in the beginning of the semester, but at least now we can have it here. So a, velocity is the first derivative, which of course you know is the slope of an xt graph, and acceleration is the first derivative of the velocity, which is the second derivative of the position. So let's put that in here. D squared x dt squared. Now let's put it in this form, d squared x dt squared plus k over m x equals 0. So how do you solve that? Well, you can't really manipulate this x as an x because it's not an x, it's the second derivative of x. So this gets into the subject of differential equations, which is you can take a whole course in that. But basically what we find is that if you have an equation of this form, okay, which is similar to this, but basically a constant number, and I'll explain why I put the omega squared here. But I could have said a, I could have said d squared x dt squared plus ax equals 0. But instead I'm putting this here because later it'll be more convenient to have it in that form. So if that's the equation, then the solutions are in the form x equals a cosine of omega t. So that's why calling this omega squared is convenient, because there's an omega in the answer. Notice this is simple harmonic motion, and the omega, of course, is radians per second. It's really the same omega as angular velocity. So let's verify that this solution solves this equation. Okay, what's dx dt? Okay, cosine becomes negative, and you put this out front. So negative omega a sine omega t. And then d squared x dt squared is a derivative of that. So this becomes cosine, and then we get another factor of omega. So negative omega squared a cosine of omega t. So let's add this all up. So negative omega squared a cosine omega t plus omega squared times x, which is a cosine omega t, equals what? Well, they just add up to 0. So yes, so basically that verifies that this is the solution. So let's compare. This was an abstract mathematical thing, but let's compare it to this. So this is our omega squared. So we expect there to be solutions of the form a cosine omega t, where omega equals the square root of k over m, because this is omega squared. Now we can express omega in terms of the period as follows. We know that for t equals 1 period, omega should equal 2 pi radians. All right. In order for that to work, then omega has to be equal to 2 pi over t, like that. Another way we write this is 2 pi f, because f equals 1 over t. So if we combine omega equals the square root of k over m and omega equals 2 pi f, or 2 pi over t, let's put it that way, we can get an expression for the period. So the period is 2 pi times the square root of m over k. So this is the period of a mass on a spring. Now let's look at a pendulum. A pendulum has a mass here, and sometimes it's extended out over here. And let's say it has a length L. So ultimately we want to A, describe its motion, and B, figure out the equation for the period of a pendulum. Alright, so the way we can do that is to use forces. Let's draw all of our forces. We have mg going down, and the force that's going to concern us is, there's obviously going to be another force here, a component of mg going in that direction, and a component going in this direction. We don't really care about this one. This is going to balance the tension here. So while it does exist, I'm just going to draw the ones that we need for the calculation. So, by the way, that's going to be the same theta. So this is going to be mg sine of theta. And it's really, if it's displaced in that direction, it's a negative force. So the force acting on the bob of a pendulum is negative mg sine of theta. So that's the force that's going to accelerate the mass. Now the mass is moved along this arc length s, and that's where it's accelerating along that arc length. So when we say F equals ma here, a is going to be d squared s dt squared. It's going to be the acceleration along that arc length s of the circle that it makes. So let's go ahead and put everything in. So we got negative mg sine of theta equals md squared s dt squared. Okay, we got too many variables here. We got theta and s. We'd like it all to be in one variable. Well, we know that from theta equals s over L, from the definition of theta, basically the definition of angular measurement in radians. So we can at least put that in. Negative mg sine of s over L equals m d squared s dt squared. So let's put it into a kind of usable form, and we get d squared s dt squared, the m's cancel out, plus g sine of s over L equals 0. And we notice that it's almost in the form that we had before for a mass on a spring. The difference is we have sine of s over L instead of s over L. So are there any conditions where this would just be s over L instead of sine of s over L? And it turns out that is the case. It's the case for small angles, because for small angles, for theta small, sine of theta is approximately equal to theta. So if you want to verify it, let's do it. So remember, we're in radian mode here. We see that 1 starts to get pretty far off, but let's test some intermediate values. 1 was 0.84. Let's try 0.5. 0.5 sine is 0.479. So you start to see some difference there. So now let's look at these in terms of degrees. What's 0.1 radians in degrees? So 0.1 times 180 divided by pi is 5.72 degrees. And what's 0.5? 0.5 times 180 divided by pi is like 29 degrees. What about 0.01 times 180 divided by pi is like 0.57 degrees. So definitely at less than a degree, I would say that sine of theta equals theta. For 5 degrees, it's still pretty close. But when you get past, when you get up to 29 degrees, we're starting to see some differences. And this is 57 degrees, so that's pretty far off. So what's small angle? So small angle could be, say, less than 10 degrees. I mean, you could actually calculate what percent off you want to be. But for small degrees, like 5 degrees, 10 degrees, or less than that, we can say that sine of theta is approximately equal to theta. So that means we can write this as, for theta small, d squared s dt squared plus, so this becomes, sine of theta just becomes just theta. So g over ls equals 0. Well, here we go. Now we got our same form where this becomes the omega squared. So we know the solutions are going to be a cosine omega t, where omega equals the square root of g over L, and using the same method we had before, where omega equals 2 pi over t, and this gives us t equals 2 pi times the square root of L over g. So this is the period of the pendulum. Notice that the period of a pendulum does not depend on the amplitude. It depends on the length of the string and the acceleration due to gravity. So if you move your pendulum to another planet, you will get a different period. If you lengthen the string or shorten the string, you'll get a different period. If you give it a different amplitude, meaning you start it further out or a little bit less out, you're going to get the same answer, except being cautious that you're always using small angle. If you use like 10 degrees and 20 degrees, you're going to start to notice a difference. All right, so that's 2 examples of simple harmonic motion. And once you have those equations, it's very easy to solve problems.